Welcome to another class of process heat transfer. In this lecture, I will talk about the heat and momentum transfer in turbulent flows. In most of the flows that we encountered in engineering practices are turbulent, and therefore it is very important to understand that how turbulence affects the wall shear stress and the heat transfer. So the turbulent flow is actually characterized by the random and the rapid fluctuations of the group of fluid particles, and that fluid particles are sometimes called eddies throughout the boundary layer. These fluctuations provide an additional mechanism for momentum and heat transfer. In laminar flow, the fluid particles flow in an orderly manner along streamlines, and both momentum and heat are transferred across streamline by molecular diffusion. But in this topic, the most interesting thing is in the turbulent flow, the transverse motion of eddies transport momentum and heat to other regions of the flow before they mix with the rest of the fluid and lose their identity. So it will enhance the momentum and the heat transfer. As a result of this, turbulent flow is associated with much higher values of frictions and the heat transfer coefficients. The presence of eddies in the turbulent flow, which actually causes significant fluctuations in the values of the velocity, temperature, pressure, and even the density in case of incompressible flows. As you can see in this diagram, that the variation of instantaneous velocity component u with the time at a specific location as can be measured with a hot wire anemometer probe or with other sensitive devices. We have observed that the instantaneous value of the velocity fluctuates about the mean value, right? And we suggest that the velocity can be expressed as a sum of the mean value, that is u bar, and the fluctuating component, that is u slash. The significance of the mean velocity and is very important, and its magnitude is very high compared to the fluctuating component. So this is the diagram which actually shows the variation of the instantaneous velocity component u, right, with respect to the time, and this is the mean value of the velocity component, and this is the fluctuating component. The mean velocity is the magnitude of the mean velocity is very high, right, and as you can see that the fluctuating component sometimes very high, right, in this case, in this direction, and sometimes very low. So we can say that when you determine the overall velocity, that the instantaneous velocity, and it is comprising of the mean velocity and the fluctuating velocity, the magnitude of the fluctuating velocity is very small compared to the mean velocity, and from the same expressions we can determine the instantaneous value of the pressure, instantaneous value of the temperatures. So consider the upward eddy motion of a fluid during the flow over a surface. So the Reynolds shear stress can be expressed by this expression, and this ut is the dynamic viscosity for the turbulent region, right, and this is the velocity gradient. And similarly we can express the heat transfer, right, for the turbulent region by this expression, and we have already studied this expression in the previous lectures. The random eddy motion of a group of particles, which actually resembles the random motion of the molecules in a gas, which are actually colliding with each other after traveling certain distance and exchanging the momentum and the heat in the process. Therefore, the momentum and the heat transfer by the eddies in the turbulent boundary layer is also analogous or the similar to the molecular momentum and the heat diffusion. So the turbulent wall shear stress which basically expressed by this relationship, and the turbulent heat transfer can be expressed by this expression, right? Here in this expression, this mu t is called the turbulent viscosity, right, which accounts for the momentum transport by the turbulent eddies. Whereas in this expression, this kT is called the turbulent thermal conductivity, which actually accounts for the thermal energy transport by the turbulent eddies. So the total wall shear stress can be expressed by this expression, and this is the viscosity and this is the viscosity in the turbulent region. So if we take the density component common from this terminology and from this term, so it will become the viscosity over density, right, and this will be called the kinematic viscosity. And this terminology epsilon m, which will be the mu t divided by the density, and which will be called the momentum diffusivity, right? And similarly, the total heat transfer can be expressed by this expression, right? And if we take common, right, density and the heat capacity from this term, right, and it will become alpha and epsilon h, right? And epsilon h is simply known as the eddy diffusivity of heat. So these are the expressions for the eddy diffusivity of momentum, which can be expressed as the mu t divided by the density. And similarly, the eddy diffusivity of heat can be expressed by the thermal conductivity and kT in the turbulent region divided by the density and the heat capacity. So the eddy motion, right, and the eddy diffusivities are much larger than the molecular counterparts in the core region of the turbulent boundary layer. The eddy motion loses its intensity close to the wall and diminishes or finishes at the wall because of the no slip conditions. On the similar ground, we can say that the velocity and the temperature profiles are nearly uniform in the core region of a turbulent boundary layer, whereas it is very steep in the thin layer adjacent to the wall, resulting in a large velocity temperature gradient at the wall surface. So it is no surprise that the wall shear stress and the wall heat flux are much larger in the turbulent flow than that in the laminar flow, and it can be observed in these two diagrams, right? And in case of laminar flows, the velocity profile as well as the temperature profiles are somewhat vertical, right? And whereas in case of turbulent flow, the velocity and the temperature profile is up to somewhat more steeper and more closer towards this wall because of the eddies, which will diminishes or finishes at the surface. So the molecular diffusivities, such as this kinematic viscosity and this value molecular diffusivity, as well as the viscosity, right, and the thermal conductivities are the fluid properties, right? So the properties can be found from the literature or from any handbook, whereas the momentum diffusivity and the eddy diffusivity of heat are not the fluid properties, right? And they mainly depends on the flow conditions, right? So the eddy diffusivity of momentum and the eddy diffusivity of heat decreases towards the wall, becoming zero at the wall. The eddy diffusivity of momentum as well as the eddy diffusivity of heat decreases or minimizes at the wall, and ultimately it will become zero at the wall. In this topic, I will talk about the laminar flows in the tubes. As we have studied earlier that the flow in the tubes is a laminar if the Reynolds number is less than 2300, that the flow is fully developed if the tube is sufficiently long, such as the relative to the entry length, and so that the entrance effects are negligible. In this section, we will consider the steady laminar flow of an incompressible fluid with constant properties in the fully developed region of a straight circular tube. We will then obtain the momentum and the energy equations by applying the momentum and the energy balance to the differential element that is here in the circular tube. Then we will obtain the velocity and the temperature profiles by solving those equations. Then we will use them to obtain the relationships for the friction factor as well as the Nusselt number. An important aspect of the analysis is that one of the few available for the viscous flow and the forced convection. As we have studied the laminar flow, that in the fully developed laminar region, each fluid particles moves at a constant axial velocity along a streamline, and then the velocity profile in the fully developed region will remain unchanged in the flow direction, right? This is particular example of the fully developed flow, laminar flow in the tube, and the velocity profile will remain unchanged in the flow direction. There is no motion in the radial direction, and this is the axial direction, this is the axial direction, and this is the radial direction. The flow is only in the axial direction. There is no flow of the fluid in the radial direction, and thus the velocity component v in the direction normal to the flow is everywhere is zero, right? There is no acceleration since the flow is steady. So the flow particles are moving at a constant speed. There is no acceleration or deceleration. So this condition is called the steady flow. Now consider this is a pipe, right? And the flow of the fluid is inside the pipe is fully developed, right? And we will now consider a ring-shaped differential element or the differential volume whose radius is r, right? And this is r, and this is the differential element, and its radius is r, and its thickness, this differential element thickness is dr, where the length of this differential ring or the differential element is dx, right? The pressure force which is acting on this differential element, right, is actually the product of the pressure, right, multiplied by the surface area. Now we will use the same expression, right, the product of force, or sorry, the product of pressure multiplied by the surface area will actually give us the force balance. Now we are going to apply a force balance on the volume element in the flow direction. So this is actually the force balance on the volume element in the flow direction, right? And this is actually the pressure at point x length, and if we multiply by the area, this will become the force at point x length, right? And similarly, if we apply the force balance at x plus x, so this is the pressure at x plus x length, and if you multiply by the area of the differential element, so this will give us the force at this length at x plus dx. Similarly, if we add another force which is applying on the element that is known as the tau tau is actually the shear stress, and shear stress has the same unit as the unit of pressure, right? So the shear stress is the force per unit area. So this is the shear stress at the radius r, and if we multiply by the area of this differential element, so we will get the force or the shear force at the radius r of the differential element, minus we will, if we apply the same balance, that the shear stress at the radius r plus dr, and if we multiply by the area of the differential element, so this whole expression will give us the force or the shear force at the radius r plus dr. And if we simplify this equation by dividing 2 pi dr dx, we will have this expression. And if we take the limits from dr or dx approaches to 0, and according to the definition of first principle, we will have this expression. Now if we substitute the value of tau, which is actually minus mu and the velocity profile, and we can rearrange the above equation in this way. So this will be the rearranged equation, right? And if we add or if we substitute the value of the shear stress, if we add the value of the shear stress in this equation, and after simplifying that, we will have this expression. And if we integrate this expression twice, we will have this expression. The integration is very simple and straightforward. First you have to integrate first time, and you will have this constant C1, and if you integrate the same equation for the second time, you will have the constant C2 here. This is the expression that you will get after integrating twice of this expression. So it will have two constants, C1 and C2. This will be the indication that you have integrated this equation twice, and you will get two constants, C1 and C2. This expression is actually the velocity profile in terms of the radius, right? Now you have to get the values of these two constants, C1 and C2. So in order to get the values of these constants, C1 and C2, you have to put the boundary conditions. Like the velocity profile, the VR, is obtained by applying the boundary conditions. The first boundary condition is the change in the velocity with respect to the change in radius. So this is the expression, or this is that we have said at the start of the topic, that the velocity is not changing. The velocity is not changing in the radial direction. Velocity is only changing in the axial direction, that is on the x direction, right? And at r is equal to 0, which means at the center the radial velocity is 0. This is the first boundary condition because of the symmetry about the center line. The second boundary condition is, which is the velocity is equal to 0 at r is equal to capital R. When the radius becomes the capital R, which is the radius of the tube, and this R represents that you are at the wall, and at the wall we have said that there is no slip condition at the tube surface, so that at the tube surface, inside surface, there is no slip condition at r is equal to r, so the velocity would be equal to 0. And if we put the boundary condition in the previous equation, and we will have this expression for the velocity profile. So in order to get the mean velocity of the fluid which is flowing inside the tube, this is the formula, and the limits are also given, and it is a function of the velocity as a function of r and x, radial direction and the axial direction, and r into dr. This is the expression, and no need to remember any kind of expression. And in the exam, if you get any numerical related to it, the lengthy formulas will always be given in the exam. No need to memorize, but you need to keep in mind that how to solve these numericals, or how to solve these velocity profile expressions. So this is the expression of the mean velocity, and you have to put the value of the velocity profile from this expression. If you put this velocity profile expression in this expression, and after integrating it from 0 to r, you will get the value of the mean velocity, and this is actually done over here, right? And this is the simplest integration, that after putting the expression of the VR that we have developed in the previous slide, and after integrating it from 0 to r, you will get the expression which is like this one. This is the expression for the mean velocity. And if you compare the equations, that the velocity profile and the mean velocity, you will have this expression. So this velocity profile is also the function of the mean velocity. So either you have the mean velocity, right? Is, for example, if you have the value of the mean velocity and you want to determine the velocity profile at some radius at any point in the tube, so you will just put the value of r. This capital R is actually the radius of the tube, which is also given, so you can easily get the value of the velocity profile in the radial direction. So it is convenient from the velocity profile, since the Vm can be determined easily from the flow rate information. So the maximum velocity occurs at the center line, and it is determined from this equation after substituting r is equal to 0. And if we put r is equal to 0 in this expression, so this part will become 0, and whole part in the parenthesis will become equal to 1. So at the center line, the velocity or the profile will be equal to the velocity will be the maximum, and it will be equal to 2 times the mean velocity. Or simply you can say that if you divide this 2 on the other side, so you can say that at the center the mean velocity is half of the maximum velocity. Now let's discuss about the pressure drop. It is a quantity of interest in the analysis of tube flow. The main thing is the pressure drop, which is delta P, right? And since it is directly related to the power requirements of a fan or a pump to maintain the flow, so therefore it is very important to determine the pressure drop in the equipment. So it will ultimately determine how much power is needed to flow the particular amount of fluid in that particular equipment. So there are simple expressions which are given, and for the laminar flow, that the pressure drop can be expressed by this equation, right? And it is very simple. Whereas the pressure drop in the all other types of internal flows, such as laminar or turbulent flows, which will be ultimately related to this expression. So in this expression, some parameters are very important to understand, that this is the delta P, and this is the length of the tube, and this is the diameter, this is the density of the fluid, and this is the mean velocity of the fluid, right? And the one of the most important parameter in determining the pressure drop is the friction factor, which is also called the Darcy friction factor, right? And which is actually comes after the French engineer Henry Darcy. And this is the friction factor F, and it is different than the coefficient of friction. Coefficient of friction is simply represented by CF. So CF is different, and this is the friction factor. So the friction factor is an important parameter which will tell us that whether it is connected with the laminar flow or the turbulent flow. So in the next page, this is the particular expression for the friction factor, and the friction factor is connected with the Reynolds number. So for the laminar flow in the circular tube, we can use this expression and to determine the friction factor, and then after getting the friction factor we will put the value of the friction factor in this expression and putting all other remaining parameters, and we will get the value of the pressure drop. This equation is actually shows that in the laminar flow the friction factor is a function of Reynolds number only, and it is independent of the roughness of the surface. Once we will have the value of the pressure drop, the next is we have to determine the pumping power which is required for that particular operation. In order to determine the pumping power, we will use this expression. This is the volumetric flow rate, and this is the delta P. When we put the values of volumetric flow rate and the delta P in this expression, we will get the value of the pumping power, right? So this volumetric flow rate further connected with this famous equation or the famous law, which is called the Poiseuille equation or the Poiseuille's law, and it is also called the Hagen-Poiseuille flow, and it is in honor of the works of G. Hagen and J. Poiseuille on this subject, which is related to the flow of the fluid in a particular tube, which is ultimately leads to the determination of the delta P. So here the one thing that is very important, that for a specified flow rate and for the specified value of the pressure drop, the required pumping power is proportional to the length of the tube and the viscosity of the fluid, but it is inversely proportional to the fourth power of the radius or the diameter of the tube. So keeping the two parameters, that is the flow rate and the pressure, if these are constant, so the pumping power will mainly depends on directly related to the length and the viscosity, and inversely proportional to the radius or the diameter of that particular tube. This is actually the comparison that if we have a tube of diameter D, right, and its pumping power will be equal to 16 horsepower. So what we will do is we will simply double the diameter of the tube, right? So what we will see that the pumping power is reduced 16 times. So the pumping power requirement for a laminar flow piping system can be reduced by a 16 factor by doubling the diameter of the pipe. So here we will see that the turbulent flows in the tubes. So for the smooth tubes, so if the surface of the tube is smooth, so this is the expression that can be used for the determination of the friction factor, and it is the function of the Reynolds number. So you can use this expression for the smooth tubes if the Reynolds number is in between the value of 10 raised to the power 4 and less than the 10 raised to the power 6. So if the Reynolds number is in between this range, you can use this expression, and after using this expression you can put the value of the friction factor in this expression. You will have the value of the Nusselt number. Once you will have the value of the Nusselt number, you can get the value of the convective heat transfer coefficient. So the whole procedure that we are doing from last few lectures, that the determination of the heat transfer coefficient is very crucial parameter, and it will goes through multiple steps, and this is the final step where you will put the value of the Reynolds number, the Prandtl number, or the friction factor for a particular Reynolds number, and you will get the value of the Reynolds Nusselt number, and from the Nusselt number you will have the value of the convective heat transfer coefficient. If the Prandtl number is in between the range of 0.7 and 160 and the Reynolds number is greater than 110,000, then you will be able to use this expression of the Nusselt number that is given here. And for the different Reynolds number or the different Prandtl number, if the Prandtl number which is in between the range of 0.5 to 2000 and the Reynolds number is in between this range, you have to use this expression for the Nusselt number, and after getting the value of the Nusselt number you will have to determine that convective heat transfer coefficient. So there are multiple expressions which are given here, but the boundary conditions or the limitations are also given in the sideline, that if you have to use this expression, you will have to see that the flow conditions, if the flow condition lies in between this range or in this range, you will have to use that particular expression for the Nusselt number, and then the Nusselt number will be used to determine the other parameters such as the convective heat transfer coefficients.